Next talk is by Kunshan Wang, together with Steve Blackburn and Peter Zhu and Matthew Valentine from ANU and Google and Shopify. And Kunshan will give the talk.
Yes. Yes. Thank you. So this research is a collaboration between the ANU and Shopify, and CRuby is the Ruby implementation that powers this company. And let's start. And this talk is dedicated to Chris Seaton. He was our collaborator at Shopify, and he started this project, but unfortunately, he passed away 2 years ago. And this talk is a practitioner report. We will introduce our experience of integrating another GC implementation into CRuby, and in this case, this is MMTK. And I can assure you, this is full of challenge. And let's talk about CRuby. Mr. Matsumoto Yukihiro created the Ruby programming language in 1995, and it started with a pretty standard mark sweep GC algorithm. But there's one peculiar aspect of this algorithm, is that all objects are 40 bytes in size. Strange. You may ask, one size doesn't fit all. What about big strings, and what about big arrays? And CRuby's answer is just call malloc. Yes, the malloc in C standard library. You see, when an object needs more memory than that, it will allocate its payload using malloc and let the GC object hold raw pointer to those buffers. And some GC objects even hold multiple such buffers. But the CRuby GC is constantly evolving. In version 2.1, it introduced generational GC. Because it's still non-moving, it uses in-header sticky mark bit to denote those objects. And in version 2.7, introduced compacting GC. This allows objects to be moved around to mitigate fragmentation. And in version 3.2, it introduced variable width allocation. Now objects come in multiple size classes, and slightly larger objects can now fit into the GC heap in larger size classes. But despite continued development effort, the CRuby GC is still not 100% satisfactory. The compaction is still costly, so it's triggered manually. The objects are still limited to 640 bytes, and GC is still single-threaded. Then what can we do? Of course, we can continue to improve CRuby's GC, and we can also do something radical, such as we rewrite the GC from scratch, or we replace it with an existing high-performance GC. But we don't think replacing the GC is a good idea. Instead, the more rational approach is to extract the interface between the VM and the GC so that CRuby can adopt other GCs if they want, including MMTK and anything else. And let's talk about MMTK. MMTK stands for Memory Management Toolkit, and is a framework for garbage collection. It comes with lots of garbage collection algorithms, and it supports parallel GC and comes with performance analysis tool. But this talk is not about MMTK, it's how to get CRuby work with another GC. If you are interested, please you are welcome to visit our website. So now we have CRuby and we have MMTK, and shall we just plug MMTK into CRuby and expect them to work directly? Not yet. Note that this project started in year 2020, at which time CRuby still didn't have a modular GC API. So before integrating MMTK, it's our job to identify the GC interface in CRuby, and we do this in multiple steps. Step 1, we support no GC that we allocate but don't collect. And in step 2, we support non-copying GC, and step 3, we support copying GC, and in step 4, we support generational GC. And in each of the steps, we identify part of the VM GC interface, and in step 3 and 4 specifically, we use emix and sticky emix GC algorithm because CRuby needs object pinning. And we have faced many challenges, but limited by time, this talk we are going to omit some of the challenges and only go deep on some of the selected challenges. And if you need more information, you can always read the paper. Also, let's start with part 1, no GC and the allocation interface. So do you see the function over there? CRuby called that function to allocate heap objects. So just wire that function to MMTK and we are almost done. And then we just need to do lots and lots of trivial work. And luckily, I don't have to do any of them. So thank you, Angus Atkinson, a student at ANU who initially worked on this project. With his work, we were able to run Rails on CRuby with MMTK with no GC. And then let's proceed to part 2, non-copying GC, where I took over this project. In this part, we dealt with stopping mutators for GC, stack scanning, and object scanning. But this part is kind of easy because we can mostly reuse CRuby's existing mechanism with minor additions. And it worked. CRuby can work with MMTK and a non-moving GC. Let's proceed to part 3. And this is copying GC and reference forwarding. So reference forwarding means when the GC moves an object, you need to update its field so that it points to the new address of the object. Supporting reference forwarding itself easy. We just wire this function to those functions, and that's done. But the real challenge is that in CRuby, some fields cannot be updated. Yes, the object has fields, and some of the fields cannot be updated. You may ask why. To answer this question, we need to go to the history of CRuby's GC. CRuby started in 1995 with a non-moving mark sweep collector, but it didn't get moving GC until 2019. So during the 20 years in between, the Ruby community thrived. Third-party gems were developed, and CRuby runtime grew, but none of the legacy code written in this period were aware of moving GC. And because CRuby is written in C, the developers define object layout in terms of C structs. And to identify the reference types, the developer provide a so-called marking function to visit those reference fields. However, to support copying GC, moving GC, the old style marking function must be rewritten in a style that allows fields to be updated. This may mean that the developer may have to rewrite the marking function of all the legacy types. Or do they have to? But that's a lot of work, a lot of legacy code. So instead, the developers found a way to allow graceful transition. They allow legacy objects and modern objects to coexist. So the legacy object on the left-hand side couldn't update their fields, so they pinned their children, so there's no need to update their fields. On the right-hand side, the modern object can update their fields, so their children can move freely. And in CRuby's mark compact garbage collector, it will start tracing, while during tracing, it identifies those unupdatable fields and pin their children. So during compaction, they can move all objects except the pinned object. However, this simple idea doesn't work for MMTK's image collector because image is a scavenging GC. In simple terms, a scavenging GC copies object during tracing rather than after tracing. So during tracing, if the scavenging collector happens to visit the fields in the wrong order, for example, it visits this field first and moves the object, and then it visits this field, but it finds the object is moved, but it cannot update this field. So to support scavenging GC, we must pin object before tracing starts. So in order to do this, we need to identify all objects that has unupdatable fields, and we call such objects potential pinning parents, or PPP for short. And when using image, during moving GC, because we identify the PPPs, we pin their children before we start tracing. You see, the tracing can update some of the objects, but not the pinned objects. And it worked. Now CRuby work with MMTK and a moving image collector. And we can proceed to part 4, generational GC. To support generational GC, it's important to identify the remembered set, that is the references from old to young objects. There are many ways to do this, and one way is to use the object remembering barrier. When assigning, we just remember the source object so that during the next nursery GC, it conservatively treat their fields as roots. Supporting write barrier is easy, just wire that function to that function is done, but the real challenge is that CRuby never applies write barrier to some of the objects. Those objects are called write barrier unprotected objects, or WB unprotected objects. But why does such object exist in the first place? Let's look at the history of CRuby again. Oh, you may say, I know the history. It's just legacy code again. Yeah, you are absolutely right. Legacy code is one part of the problem, and the other part is the poorly designed API. So you see, CRuby allowed the Ruby method to be defined in C, but it also has some legacy unsafe API that exposes raw pointers into the guts of objects and allows C code to assign to those fields without write barrier. Of course, there are safer alternatives, but some legacy code in the wild are still using those unsafe deprecated APIs, so the GC has to be aware of their presence. But fortunately, handling WB unprotected object is not that hard. We just treat them as if they have been updated before every GC, and this effectively keeps them in the remember set until the next full heap GC. And we made it. We have gone through all the steps and faced most of the challenges. Now CRuby work with MMTK with sticky image. Oh, we should celebrate. Or should we? So when we measure the performance, it still sucks. So something is still not right. So in the end, we still need to face the remaining challenges. One is identifying the GC performance bottleneck, and the other is, wait for it, finalizers. So finally, let's go to the ultimate challenge, finalizer. A finalizer is an operation to be performed when an object is determined to be dead. It comes in many programming languages, and in CRuby, it's in the form of this obj-free function. And the real challenge, almost all objects in CRuby are subject to finalization. You say, that's madness. Finalization should be only be for a small proportion of all objects, but what's happening in CRuby? So to really remember, the CRuby has an object size limit. CRuby's default GC is simply incapable of allocating any objects larger than 640 bytes. So if an object needs more memory than that, it uses malloc. Then the immediate question is, when do we free this malloc buffer? And the answer is, when this object dies, of course. You see, this is finalizer semantics. When object dies, do something. And in this case, it's freeing this buffer. So in CRuby, any objects that have associated malloc buffer are subject to finalization. So what objects? Well, almost all objects. Almost all types in CRuby have malloc buffers for one reason or another. So for this reason, the GC has to look at every single dead object just to see if they have associated malloc buffer and free them. And how bad is this? Well, we run the Liquid benchmark with MMTK plus Emacs, where Liquid is the templating engine. And we use an eBPF-based visualization tool to make a timeline to show what exactly is happening during a GC. So you see, the GC can traverse the whole heap in a very short time, but spend much more time just calling the obj-free function on the dead objects. Okay, you can ignore that. So you may ask, this is single-threaded. What about you parallelize it using MMTK's worker threads? Well, if we parallelize it, it's even worse. So let's tidy up a bit. So just by calling that function in multiple threads, the performance degraded. This is quite counterintuitive. So why doesn't this finalization function scale? And the culprit is free. Yes, the free in C standard library. You should remember this I just called malloc. So seriously, we did a micro benchmark that freed 100 million small objects in multiple threads. We tried multiple malloc implementation that the more threads we have, the slower it becomes. And malloc is the only implementation that scales, but only accelerates to a factor of 4. And obj-free is all about calling free, so no wonder this thing doesn't scale. So what can we do about this? If we can't parallelize it? Answer is we just get rid of it. So in other words, we refactor CRuby so that is to make it unnecessary to call free. So how do we do this? Remember, CRuby has a size limit, but MMTK doesn't. MMTK doesn't have a size limit. So instead of allocating those buffers in malloc, we just allocate this in GC heap and let the GC handle both the header object and the payload without using finalizer. And we inspected the distribution of dead objects, and we chose to refactor 3 types. They are string, array, and regular expression match data, so they don't use malloc. So instead of using malloc, they allocate their payloads in the GC, and they don't need finalizer anymore. And the result, very obvious. You see the finalization is become much smaller compared to transitive closure. But remember, this is Emacs. When we switch to sticky Emacs, the transitive closure bus becomes much faster and finalization becomes the bottleneck again. So now we have already gone through all the challenges and steps, and what have we learned? History lesson, maybe. CRuby started with a non-moving, non-generational, blah, 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 but we are now aware of them. But I think it's a bit too late. Now we have to deal with potential pinning parents, right barrier unprotected object, and eliminate unnecessary finalizations. But what if CRuby started with a generational copying GC? If we engineer for a high-performance GC from the get-go, we won't need to deal with those challenges now. So let's read the overarching lesson aloud. Assumptions about GC, such as non-moving, non-generational, limited object size, etc., can bake bad design into the VM during early development, which make them more costly to fix in the future. And status quo, we are closely working with CRuby developers, and in fact, two of our authors, one thing there, are CRuby committers. And in version 3.4, CRuby finally got an official modular GC API and official MMTK binding. So let's end this talk by saying GC is important, and let's do it properly. Thank you.
Okay, so any questions? Yeah.
Thank you. I will. Hello, Jeremy Singer, University of Glasgow. Thanks for a really nice talk and a very nice layout of the different challenges. I wonder whether there's any potential for a kind of standardization of the GC interface. You know, whether it's kind of with POSIX or somebody like that, you know, a kind of very well-defined set of functionality and APIs that are needed so that new VM designers or people retrofitted things like yourself can work within a common framework. Is that something you've thought about?
Well, such things, I think it's nice to have. Currently, we don't have this thing. But to find this thing, we need to, for example, investigate multiple GC algorithms to see what they need from the VM. And we need to investigate multiple VMs, and because each VM has their own characteristics and what they need from the GC. And we also need knowledge about the state-of-the-art VM implementation to know what's the best practice so that we can eventually come up with a nice interface for that. And we are working on it.
Tim Harris from OpenAI. I really love the presentation here and all of these problems that came up, and then the next problem comes up and so on. And I was wondering if we had a slightly different GC, whether there'd be some more problems coming up on the list. So let's say we wanted to introduce a parallel collector or concurrent collector. Does that add any extra requirements beyond the one here?
Yes, definitely. Let's take a concurrent GC for example. If we need concurrent GC, we will make sure that the GC will synchronize with the mutators, and so that the right barriers are needed. So if a language that doesn't insert a right barrier properly in all the cases, it will be in trouble and probably need some refactoring. And similarly true for like other kind of GC.
Thanks. Really nice talk.
Yeah, thank you.
Yeah. Any more questions? Okay, so let's thank the speaker.